Okay, hi everyone. This is the last lecture of CHEN 422, Chemical Reaction Engineering, and today I'll just be solving the problem set, your final problem set for the course, and your exam will come from this problem set, or 90% or 80% of your final exam will come from this problem set with a few modifications, and the remaining points will be sort of a harder version or a variation of these problems. Okay, so let's get started here. So I'm going to start, and again, all of these problems are taken from your previous homeworks. None of them are new. And it's just encapsulates all of the topics we covered throughout this course. Okay, let's get started here. So let me share my whiteboard. Let me switch off this camera and let's start. Okay, so problem number 1. You're given a fluid FCC system, right? This is okay, you're given an FCC system and you're given a bunch of information. So you're told that you have 50 tons. So you have catalyst is equal to 50 tons. And the density of this catalyst is 800 kilograms per meter cubed. The feed is about, so you have a feed, which is 38,000 barrels per day, which is equivalent to 6,000 meter cubed per day. And the density of this feed is 900 kilograms per meter cubed. Okay. And you're being told it's cracked so that you get long chain hydrocarbons. You crack the long chain hydrocarbons into shorter hydrocarbons, and you're given a bunch of equations, and you're being told that 60% of the vaporized feed is cracked in the unit. What's the rate of the reaction expressed as moles reacted per kilogram catalyst second and moles reacted per meter cubed catalyst second? So we're being told that the conversion is 0.6, and you just need to find the reaction rate in this problem. Okay, so for this problem, basically your first reaction rate you're looking for, just look at the units. So the first rate you need to find the reaction rate, which is minus R prime, which is in units of moles reacted per kilogram catalyst second, right? So if my feed is 6,000 meter cubed per day, density is kilograms per meter cubed. I need to find basically a molecular weight to get moles reacted using this conversion. So let's first of all find the mass of the feed. It is 6,000 meter cubed per day multiplied by 900 kilograms per meter cubed. And then I'm going to convert this day to second. So you have 1 day over 24 hours, 60 minutes, 60 seconds. And this should give me a mass flow rate of 6,000 multiplied by 900 divided by 24, 60, 60. And I get a mass flow rate of 62.5 moles per second, right? Sorry, 62.5 kilograms per second, actually, 62.5 kilograms per second. And then I need to convert this to moles. And in the problem, you're being told to use C20, H42 as the representative molecule, and this molecule has a molecular weight of 282.9 moles per gram, right? There's actually just 282 grams per mole, sorry. I read this 9 incorrectly, so I have 282 grams per mole, and then I'm going to convert this number into moles. So now N feed is 62.5 times 10 to the 3 grams per second, right? 62.5. Let me write this properly. So I have 62.5 grams per second multiplied by 1 over 282 moles per second, 6 kilograms, right? And you also, so this is just 1,000, so that's multiplied by 1,000 divided by 282, and you should get 221 moles per second. So this is the moles of the feed. You're being told that 60% is cracked, right? So the number of moles which actually reacts. So N reacted is 221 multiplied by 0.6, and this is equal to 132.6 moles per second. So for this one, I need moles reacted per kilogram catalyst second. I have 50 tons, which is equal to 50 times 10 to the power 3 kilograms. So this ratio here will be 132.6 divided by 50 times 10 to the 3, and this will be 0.00265 moles reacted per kilogram catalyst second. Okay, this is the first expression. The second expression this problem is asking for is moles reacted per meter cubed catalyst second. So it's R triple prime, and this is moles reacted divided by meter cubed catalyst second, and this should be minus because the moles reacted. So now my moles reacted will be the same, which is 132.6 mole per second divided by the meter cubed of catalyst. So I have 50 times 10 to the 3 kilograms. So volume, or I guess it's not. Let's rewrite this properly. The volume of the catalyst in this case will be, sorry, 1 second. So volume, and this is catalyst as well. This will be 50 times 10 to the power 3 kilograms divided by 800 kilograms per meter cubed, and this will be 50,000 divided by 800. This number will be very conveniently 62.5. 62.5 meter cubed catalyst. So this multiplied by 1 over 62.5 meter cubed catalyst. And for the second number, I'm going to get 132.6 divided by 62.5, which is 2.12. 2.12 moles reacted per second meter cubed. Okay, this is how you approach this problem again. It's a very simple problem actually, but try not to overthink it. Very basic concept here. Okay, let's move on to the next problem. Let me share the problem screen now. Okay, problem number 2. (1150 Kelvin N nonane thermally cracks 20 times as rapidly as at 950 Kelvin. Find the activation energy of this decomposition. Again, very basic. You just need to remember the basics and, not overthink it or trip yourself with these types of problems, right? So this is problem number 2 now. Okay, in this problem, you're being told you're given 2 temperatures. Temperature 1 is 150 Kelvin, and temperature 2 is equal to 950 Kelvin. And you're being told that R1 is 20 times R2, and you need to find the activation energy, right? So you just recall the equation where we said ln R2 over R1 is equal to E over R 1 over T2 or 1 over T1 minus 1 over T2. And the thing to remember about this is if I have R2 over R1, then T1 minus T2, sort of the order is somewhat reversed, right? So a very common error is to just have R2 over R1, T2 minus T1. And again, this is basic, so R2 over R1 will be, R2 over R1 will be 1 over 20. So then 1 over 20 is equal to E over R, 1 over 150 minus 1 over 950. And from this case, I can get E over R to be equal to 1 divided by 150 minus 1 divided by 950. Then you will get E over R to be 16364 joule, or actually this only has units of Kelvin, right? So this expression only has units of Kelvin. E over R, let me write this properly. So I have 16364.2, and this is Kelvin, because this is Kelvin, right? This is 1 over Kelvin, you cancel out and you get a dimensionless entity here, and ln is a dimensionless entity, so that's fine. And R in this case will be 8, and always remember the value for joule per mole Kelvin. So if I, cross multiply on all of this stuff, I'm gonna get, so from here I can get E to be equal to 136,051 joule per mole, right? And again, this is joule per mole Kelvin, so this joule per mole, the joule per mole cancels out and I get units of Kelvin. So E, or the activation energy, has units of joule per mole, and you can always write it as kilojoules, so it will be 136.051 kilojoule per mole. Okay, and this is the answer for problem number 2. Again, very simple problem. You just need to not confuse yourself with these types of simple scenarios. Okay, let's move on. Let me share the screen again. We are 10 here. Okay, the maximum allowable temperature for reactor is 800 Kelvin. At present, our operating set point is 780. 20 Kelvin margin of safety to account for fluctuating feed, sluggish controls, etc. Okay, so you're operating at 780 K, your maximum allowable temperature is 800 Kelvin, and you give yourself a 20 Kelvin margin of safety, etc. Now you have a more sophisticated control system. You want to raise your set point to 792, right? You say, I can control the system better, so I want to reduce my margin of safety with the same margin of safety that we now have. Okay, so you're increasing your set point, but you're still keeping the same margin of safety. That's fine. By now, how much can the reaction rate, hence production rate, be raised by this change if the reaction taking place in the reactor has an activation energy of 175 kilojoule per mole? So you want to find out, well, now I'm changing my set point from 780 Kelvin to 792 Kelvin. How faster will this reaction happen? Okay, let's go to the whiteboard here and let's just approach this problem. And again, very simple problem. Just need to be able to translate all of this text into problem solving. Really, there isn't much to it. Okay, so, and again, this idea or this equation where you have ln R2 over R1 is equal to E over R of 1 over T1 minus 1 over T2. Basically, and we've seen this even in later chapters when we're talking about temperature control. This equation, it's a simple equation. However, you can't afford to, not have it at the top of your head or not be able to use it. It's one of the very basic equations and one of the very basic thermodynamic principles. You just need to know at this level. Okay, so you're given two temperatures. The initial temperature is 780 Kelvin. Now we have a fancier control system. We raised our operating temperature to 792 Kelvin, right? 792 Kelvin. You're being told the activation energy is 175 kilojoule per mole. 175 kilojoule per mole, and this is equal to 175,000 joule per mole, right? And you basically need to find R2 over R1 equals what? And again, this, as you can see, very basic. So I have ln R2 over R1 is equal to 175,000 divided by 8.314, and just be careful of the units. 8.314 is joule per mole Kelvin. So 1 over temperature, temperatures have to be in Kelvin. So 1 over T1, which is 780, minus 1 over 792. And this, so this is in the units of this guy here are 1 over Kelvin. Units of this guy here are joule per mole. And one of the basic things to check if you're on the right track, especially when you have a lot of complex equations, maybe not this one, this is a very basic one, but when you're dealing with complex equations, check for dimensional consistency, right? If your numbers are dimensionally consistent, then most likely your calculation is correct. So in this case, ln R2 over R1, if you plug in these numbers, you should get 0.4088, and this translates to R2 over R1 to be equal to 1.505, right? So how much can the reaction rate be raised? So the reaction rate is going to increase by 50%, right? And this is what this shows right here. So maybe you can add a comment if you want to, but basically this is the answer for this problem. Good. Let's move on to the next one. Okay. Problem 4. For a given reaction, on doubling the concentration of reactants, the rate of reaction triples. Find the reaction order. And this, I don't know if I'm remembering this correctly, but this seemed to be a problem that tripped up a bunch of people for some reason. Again, in its principle or at its core, it's a very simple type of problem. However, the wording can make it a bit complex. Okay, which problem is this? This is problem 4, right? So again, so we're being told on doubling the reaction, on doubling the concentration of reactants, the rate of reaction triples. Okay, find the reaction order. So it doesn't matter. So let's say I have a reaction minus RA, and this is equal to K Ca to the power n. It could be, you know, KCa Cb to the power n. It really does not matter. And you're being told that Ca1 is equal to, or you know, Ca2 is equal to 2Ca1. And this basically translates to doubling the concentration of reactants, right? Doubling. Ca2 is equal to 2Ca1. And even if you have, you know, Cb2 is equal to 2Cb1, even if it's C to the power n and Cc2 is equal to 2Cc1, it does not matter really, because basically um, this 2 is going to factor out, 2 to the power n is going to factor out, right? Unless, you know, you have different orders here, then it might be a bit complex, but the math will reduce. But anyways, for this case, the easiest way, maybe I should have put it in the problem statement, but anyways, this comes on the test. I'll mention it in the problem statement. But let me just put a fact here. So this is a first order irreversible reaction, right? A goes to R. And this will be if the problem shows up, right? Okay, I'm assuming some people just look at the answers and don't listen to this video. Anyways, so minus RA is equal to K, Ca to the power n, and you're being told that once the concentration of reactant doubles, the rate of reaction triples, so RA2 is equal to 3 minus 3 RA1 minus, doesn't matter, right? But this is how it is. So you're being told that rate of reaction triples. Good. So in this case, I'm gonna get, so what do I need to find? I need to find the order of reaction, so I need to find n. Okay, so let's write down. So I have minus RA1 is equal to K, Ca1 to the n, and then I have minus RA2 is equal to K, Ca2 to the n. I divide these two guys, so I get RA1 over RA2 is equal to Ca1 over Ca2 to the power n. RA1 over RA2 is equal to what? 1 over 3, right? Ca1 over Ca2 is equal to half to the n, and basically you just solve for n, right? Right, so I'm gonna get basically 1 over 3 is equal to 1 over 2 to the n. So 2 to the n has to be equal to 3. So in this case, n will be, or you know, how do you solve this algebraically? And this is simple, but you need to remember how to do these things, you know. Sometimes you freeze when you see these very simple things. But anyways, let's take ln both sides. So I'm gonna get n ln 2 is equal to ln 3, right? And n will be ln 3 over ln 2. And basically n will be ln 3 divided by ln 2 will be 1.58. Good, so this is problem 4. And let me save this guy and let's move on to the next one. Are we doing a timer? 26 minutes in. Okay. Let me share the more 10. Problem 5. Liquid A decomposes by first order kinetics in a batch reactor decomposed by first order kinetics, and in a batch reactor, 50% of A is converted in a 5-minute run. How much longer would it take to reach a 75% conversion? I think this type of problem showed up on your first exam, right? Again, this is I mean, there is a good chance it might show up again, but be prepared anyways. 1 second, let me just. Okay. Let's open a new thing here. And you're being told liquid A decomposes by. Okay, this is problem 5. So I have A decomposes by first order kinetics. So A goes to R, and again, it's a decomposition, so it's irreversible. Usually you can always assume that decomposition is irreversible, right? Because once something decomposes, it's not gonna reform back to form its original components. So you're being told it's done in a batch reactor. 50%, so X of A is equal to 0.5 at T is equal to 5 minutes. How much longer would it take to reach 75% conversion? So if X of A is 0.75 now, what is the time when this will happen? Okay, so this goes back to the chapter where we were interpreting batch reactor data. So this is for chapter on interpreting IBR data, right? And in this chapter, we said for first order, so I think this was case 1, right? Case number 1 for first order irreversible reaction. The equation we're going to use is minus ln Ca over Ca naught is equal to Kt, and this translates to minus ln 1 minus Xa into Kt. And this sort of logic of solving problems shows up a lot in this course, where I have one equation and 2 sets of parameters. I use the first set of parameters to solve for the unknown, and then I use the equation now knowing the unknown variable to find, with the second set of parameters, to find whatever you need to find, right? So this is what's going to happen. So I'm going to use the first set of parameters here. Maybe green and red is not the best combination, but you know, that's how it is. 1 minus 0.5 is equal to K into 5. And from here, you can get K to be minus ln 0.5 over 5. And then I'm going to plug this parameter into the second situation. I'm going to have minus ln 1 minus 0.75 is equal to K now, which is minus ln 0.5 over 5 multiplied by T. And you solve for T, so you're going to get T to be equal to 10 minutes. Is that correct? Let me double check. So I get ln 0.25 multiplied by 5 divided by ln 0.5. And yeah, it will be 10 minutes. And this is basically the time. And you know, sometimes the problem asks you, how much longer does it take? So this is 5 minutes, so it's 5 minutes longer. And you can always put this comment here, 5 minutes longer to move from x 0.5 to x 0.7. You can always add this comment. It shows, I mean, it just shows that, you know, you're mentally present, right? Okay, let's move on to the next problem. Problem number 6. Repeat the previous problem for second order kinetics. That's fine. So this is problem number 6. And you're being told to repeat the previous problem for second order kinetics. Okay, let me recall the previous problem. So we have, we said we have, so we have XA is equal to 0.5 when t is 5 minutes, and XA is equal to 0.75 time is equal to what? And now I have second order irreversible reaction. Basically 2A goes to R, right? Okay, so for this type of problem again, you need to recall this is case number 2, right? So case number 2, if you recall it, we had 2 situations for case number 2. We had the situation when it was bimolecular. And bimolecular basically means I have A plus B goes to R, which is the product. And again, A plus B goes to R. This is a second order irreversible reaction. And the other case is unimolecular, which is 2A goes to R. So, you know, they're both second order irreversible. However, they have distinctly different equations, right? So just be careful, you know, where to locate each relevant equation in the slides. You know, for this case, when it's bimolecular, I have a M, which I need to account for. For this case, is just straightforward, right? So it's going to be the unimolecular case for this problem. And the governing equation or the problem or the governing, what do you call it? So the governing equation will be 1 over CA naught into XA over 1 minus XA is equal to KT. And similar to the previous problem, I'm going to use the first set of parameters to solve for K and the second set of parameters to solve for T. Conversely, you can just divide the two scenarios. So let's solve it slightly differently this time. So let's just divide the two cases, right? So I'm going to have 1 over CA naught into 0.5 over 1 minus 0.5 divided by 1 over CA naught into 0.75 over 1 minus 0.75. And this is equal to K into 5 over K into T, which is what time I'm trying to solve for. Let's call this T2. Doesn't matter. Just this is the T I'm solving for. It hopefully you're aware. If you're not sure, this is the T I'm solving for. Try to absorb the problem first before approaching it. Anyways, and you can do the same approach for the previous problem. And a common error I've seen on exam 1 is a lot of people just, you know, this is a very simple fraction, but a lot of people just seem to make very simple errors here. I guess if you're solving too quickly or, you know, trying to do things in a rushed way, it might be a problem. But anyways, if you just rearrange this, so if you just rearrange these variables, so it's 0.75 over this is 3, this is 1, so I get 1 over 3, T2 is 5, so I'm just going to get 1 over 3 is equal to 5 over T2, and from here, T2 is 15 minutes, right? So it's going to take 10 minutes longer. Basically, this translates to 10 minutes longer for X to go from 0.5 to 0.75, right? Again, very basic problem, but, you know, don't make these problems trip you up. Very easy points, right? Because these easy problems usually have a large point allocation, right? Because I don't expect you to drop points on them. Anyways, moving on, problem 7. After 8 minutes in a batch reactor, a reactant with an initial concentration of 1 mole per liter is 80% converted. After 80 minutes, conversion is 90%. Find the rate equation to present this reaction. So again, We're still in the chapter where we're trying to translate batch reactor data. And this problem for this case, you need to find the order of the reaction, right? So for this case, you need to find the order of the reaction. And this is problem 7. Problem 7. After 8 minutes in a batch reactor, so you're given Ca naught is 1 mole per liter. You're given T1 is equal to 8 minutes. XA1 is equal to 0.8. And T2 is equal to 18 minutes. XA2 is equal to 0.9. And you basically need to find n, right? Find the rate equation basically translates to find the order of this reaction. And this is really case number 4, right? This is case number 4 from interpreting batch reactor data for an nth order reaction. And we said the governing equation for these types of problems is, it's Ca naught 1 minus n, 1 minus xa to the 1 minus n, or, let me rewrite this. Or you can derive this actually. Let me write just the initial form and the final form. So the governing equation is actually Ca 1 minus n minus Ca naught 1 minus n, and this is equal to n minus 1 kt. And this functional form, if you plug in the equation for the conversion, will translate to Ca naught 1 minus n into 1 minus xa 1 minus n minus 1 is equal to n minus 1 kt, right? And you can use this functional form directly if you want to, but yeah, this is really the functional form for case number 4. Ca naught to the 1 minus n, big brackets, small brackets, 1 minus xa to the power 1 minus n minus 1 is equal to n minus 1 kt, okay? So now you just plug in your numbers in this case, right? So I have everything. I guess I'm missing the k, right? So you could use the first set, or you basically have 2 equations to unknowns, right? I have n and k unknown, and I have 2 parameters. So you can either solve for the k directly or divide the 2 equations. I'm going to divide the 2 equations. So I'm going to get 1 to the 1 minus n, and again 1. This is 1, right? Into 1 minus xa. Or let's plug in numbers in this case. So the initial x is 0.8, 1 minus 0.8, 1 minus n minus 1 is equal to n minus 1 k, and my first time is 8. And if I divide this by the second set of parameters, which is 1 to the 1 minus n into 1 minus 0.9, 1 minus n minus 1 is equal to n minus 1 k into 18, right? Let me erase this equal from here. Let's just put it properly. And let's cancel some of these. So this is 1, right? So let's just forget about this guy. N minus 1, n minus 1, k. K cancels. So now I have a straight, or somewhat of an easy problem. And if you have a calculator, you can always use it to solve this system directly. But it's basically 1 minus 0.8, 1 minus n minus 1, divided by 1 minus 0.9, 1 minus n minus 1 is equal to 8 over 18, right? You can always try to cross multiply and take lens, and I mean technically you could solve for it analytically. However, we'll just you can just iterate or use a calculator actually to solve for it directly. But anyways, let's iterate. So if I iterate in this case, and again, when you iterate, you have to make sure that n is not equal to 1 and n is not equal to 0. So you can iterate with any number except 1 and except 0, right? Because if n is 0, or if n is 0, then this equation is not valid. If n is 1, then I'm basically canceling 0 from the top and from the bottom here, and mathematically this expression is not valid. So you have to be careful. So when you iterate, your first iteration has to always be a number between 0 and 1. I recommend 0.5 as a first iteration. If you find that it's close to 0, or this ratio is close to this ratio, you can try maybe 0.75, 0.85, try to zone in. If it's far away from this, try a number greater than 1, maybe 1.5, 2, 3, etc., until you find the answer. But in this case, the answer is n equals 2. And on the test, if you get a problem like this, most likely the answer will be 2, 3, maybe 4. I'm not going to give you a very strange iteration, okay? So if you see this on the test, and of course, if you're listening to this video, the answer will be either 2, 3, or 4. You're not going to get something like 2.256 or something like that. No, it will be a very nice number, a very cute solution. Okay, let me save this. Let's move on to the next problem. Okay, so now on problem 8. First order reversible liquid reaction takes place in a batch reactor. A goes to R, Ca note is 0.5 moles per liter, Cr note is 0. Okay, after 8 minutes, conversion of A is 33.3, while the equilibrium conversion is 66.7. Find the rate equation for this reaction. Again, this is the case where I have an equilibrium first order reaction. Again, we talked about this in the later chapter as well. Equilibrium reaction, equilibrium, steady state, very distinct concepts, right? So make sure you understand the difference between them, right? Something can be at equilibrium but not at steady state. Something can be at steady state but not at equilibrium, right? And this is a very important concept to grasp in reaction engineering, right? Especially when we're only considering ideal scenarios, and when things get more complex, you have strange systems now, and you have other things happening. You have to clear this out from the beginning. Anyways, moving on. So this, I have a first order. It's actually reversible, right? This is what the problem is telling you. It's a first order reversible reaction. I have A going to R. Ca note is 1 mole per, actually 0.5 moles per liter. .5 moles per liter. Cr note is 0. No. Which problem is it? Yeah, that's correct. Ca note is 0.5 moles per liter. Cr note is 0. And you're being told that at T equals 8 minutes, Xa is 1/3, but Xa equilibrium is 2/3. And you need to find the rate equation, right? So basically you need to find N for this reaction. And not N, actually, you already know it's first order. You need to find the rate equation, right? So find the rate equation, which is basically minus Ra equal to what? And in this case, this is case number 6. So let's change the color here. It says case number 6. The governing equation for this case, if you recall, we said is minus ln of xAe minus xa over xAe, and this is equal to m plus 1 kt divided by m plus XAE. Okay, so this is the governing equation for this case. And you need to recall that M is equal to CR naught over CA naught, which in this case is equal to 0 because CR naught is 0. So this really simplifies this expression. And I have XAE and XA and XAE, right? So I'm going to get basically minus ln XAA is 2 over 3 minus 1 over 3 divided by 2 over 3. And this is equal to K, time is 8 minutes, divided by M is 0 plus XAE, which is 2 over 3. So now we just need to find the expression for K, right? Am I missing something here? 1 second. Yeah, we have to, because it's a reversible reaction, we have to clearly define the forward and the backward rates, right? So let's take a step back here and let's clearly write this out so to avoid confusion, right? Because I have A goes to R, the forward reaction, let's define it as K1, the backward reaction, let's define it as K2. So in this case, the reaction rate or minus RA will be, the rate of consumption of A will be K1 CA, right? It's the forward reaction minus however much I'm getting, which is K2CR, right? And I need to find an expression, a value basically for K1 and K2. And for case number 6, just remember that this equation right here is for K1. So for case number 6, I have two expressions. This is the first expression. And then my second expression will be K1 over K2 is equal to M plus XAE divided by 1 minus XAE, right? So I need to find both K1 and K2. Okay, so I'm going to use these two equations. I'm going to use this equation first to get K1. So if I basically do the math here, I'm going to get a K1 value to be equal to 0.057, 0.05. It's actually 77, so let's write this 0.058. Then I'm going to use this value in this equation, right? So I'm going to plug it into this equation right here. So I have 0.058 divided by K2, again, M is 0, XAE is 2 over 3, 1 minus XAE is 1 over 3. So I'm going to get the value of K2 to be equal to 0.029, right? So I have K1 and K2, I can plug them in here to get the rate expression for R. So if I do this, get these two guys, I'm going to get minus RA will be equal to 0.058 CA minus 0.029 CR, and this is the answer to this problem. Okay, so again, just remember when you have a reversible reaction, I have two expressions, one for the forward and one for the back reactions. Okay, let's go back to the homework. I should see the screen. Give this guy. Let's create a new one. Let's go to the homework. Problem 9. For the decomposition A to R, CA naught is 1. In a batch reactor, conversion is 75% after 1 hour, and it's just complete after 2 hours. Find the rate equation to represent these kinetics. Okay, so again, very similar idea. You're given two sets or two scenarios, and you need to basically find the expression or the rate equation which represents this. So let's just write down the given here first. So this is problem 9. Here we go. Problem 9. So I'm given a decomposition. A goes to R. First order irreversible reaction. You're being told Ca naught is 1 mole per liter. Again, it's a batch reactor. XA is equal to 0.75 at T equals 1. Or you can always use XA1 and T1 if you want to. And XA2 is 1, so basically complete. Complete means the conversion is 1, right? At T2 is equal to 2 hours. Find the rate equation. N equals, is it N? No, it's not N, because again, this is first order. So you basically need to find K. Right, so for this problem, I need to find rate equation or rate. Yeah, so rate equation. And this will be minus R A is equal to KCA. And again, this is a first order reaction. First order irreversible reaction. Okay. So again, first order irreversible reaction means that this is case number 4, right? And you will just use the governing equation for case number 4. If you recall, we said the governing equation for case number 4 is Ca naught 1 minus N into, or let's use the same notation we used last time, into 1 minus XA 1 minus N minus 1 is equal to N minus 1 KT, right? And you have two scenarios. You can either, you have two equations to unknowns. You can either use one to find K and then, wait one second. Let me double check something here. I think because if it's a first order reaction, it should not be case number 4, right? But my old solutions show that it's case number 4. Okay, so for this problem, the intention was, so on the test to make it maybe clearer, the intention was it's an nth order reversible reaction, right? So this is actually an nth order Ca to N. Because if it's a first order reaction, it's sort of obvious, right? You don't need two conditions. You can just solve it with one condition. Okay, but again, the intention was that this is an nth order reaction. And let me add a note here. Or basically, if you're listening, on the test, I'll make it clear that it's an nth order reversible reaction. Let me maybe. This nth order will be clear on test. Okay. Yeah, this explains why we have two conditions, an N and a K. Levenspiel likes to. This was taken from Levenspiel, and I guess it could have been written in a clearer way. But anyways, if this comes on the test, I'll make sure it's clear. And again, with case number 4 types of problems, there's always an iteration element. So you should always be ready to iterate. Whenever you write this equation down, it means you need to iterate. And you can either plug the first set of conditions, plug the second set of conditions, have two equations, two unknowns, N and K, or you can just divide the two cases by each other. And again, Ca naught is 1, so this really makes it easier because this cancels out. So I'm going to get 1 minus 0.75 into 1 minus N minus 1 divided by 1 minus 1 is 0, right? So I'm going to have 0 minus 1 is equal to basically T1 over T2. So actually in this case, you don't need to iterate because this is 1, right? So it gets rid of this guy right here. So again, very simpler variant of this problem, okay? So T1 is 1 hour, T2 is 2 hours, and this becomes my equation I'm trying to solve. So I'm going to get 0.25 to the 1 minus n minus 1 is equal to minus 0.5. 0.25 to the 1 minus n will be 0.5. And so n is what? I mean, quarter. I mean, it's basically 1 over this, right? So from here, you can see that n is 0.5, right? So n will be 0.5, 1 over square root of 0.25, right? It's 0.5. But if you really want to do it, so I can take ln both sides, so I get 1 minus n. Ln 0.25 is equal to ln 0.5. And from here, you can get 1 minus n is equal to ln 0.5 over ln 0.25, and n in this case will be. So this is half, so n will be 0.5, right? This is the answer to this problem, n is equal to 0.5. And again, because the second condition is x equals 1, because this condition x equals 1, this simplifies this problem. But this is how we solve this problem anyways. And on the test, I'll make it clearer that this is nth order reversible reaction. So I mean, if this is an nth order reversible reaction, and the order does not match the stoichiometry, then this reaction is does not match the stoichiometry, right? What did we call it? I'm gonna remember it as we're talking. Anyways, moving on to the next problem. Problem number 10. Okay, good. So for problem number 10, you are being told that given a gaseous feed, Ca naught is 100, Cb naught is 200, A plus B goes to R plus S, Xa is equal to 0.8. Find Xb, Ca, Cb. Okay, let's go to the, so we're progressing through the chapters now. This is problem number 10. Okay, so you have a gaseous feed, right? So you have Ca naught is 100, Cb naught is 200, A plus B goes to R plus S, Xa is 0.8, and you need to find Xb, Cb, Ca. Okay, so how do you approach this? So how do you approach this? So again, you're given the conversion, you're given the number of moles. One of them is obviously limiting in this case, right? So you can calculate the what's leaving on the other side, right? So I have A, I have 100 moles of A, I have 200 moles of B. How much do I get out of R? The conversion of A is 80, so I get 80 moles of R and 80 moles of S. Or you can do the table the same way you do it in chemistry. I don't know if you guys remember. Initial 0 0 reacted. So I'm gonna have 80 moles of A reacted, 80 moles of B reacted, right? And then I'm gonna have minus 80 minus 80. I'm gonna have 80 moles of R generated and 80 moles of S generated, and the final will basically be I'm gonna have 20 moles of A, 120 moles of B, 80 moles of R, 80 moles of um, 80 moles of S, right? Yeah. Sorry. Again, this is very basic stuff. This will not show up on your test. They have other important things to deal with. But anyways, so in this case, CA will be 20, CB will be 120, XB will be, how much is 80 divided by 200, and this will be 0.4. Okay, very basic. Let's move on from this junk. Let's move on to another problem. Okay. So problem 11, we plan to replace our present mixed flow reactor with one having double the volume for the same aqueous feed, which is 10 moles of A per liter, and the same feed rate. Find the new conversion. The reaction kinetics are represented below, and the present conversion is 70%. Okay, so you're given a reaction, you're doing it in a CSTR, and you want to do it in a CSTR with double the volume. You need to find the new conversion in this bigger CSTR. Good. Now we're doing more interesting problems here. This is problem 11, right? So in this problem, you're given a CSTR, with an initial volume, and you want to do it in a CSTR with double the volume, right? So V2 is equal to 2V1, right? Second CSTR is double the volume. You can draw a little diagram for yourself if you want to, doesn't matter. CA note, you're being told it's 10 moles per liter, and this does not change between CSTRs. You're being told that, also being told the flow rate. What flow rate is it? Is it molar? And the same feed rate, so I'm assuming it's the molar feed rate. It doesn't matter, the feed rate is the same, then all of them are the same, right? Assuming no change in density. But the one relevant for reactor design is FA note. And again, this does not change either. And you're being told that XA1 is 0.7, and the reaction is A goes to R, and minus RA is equal to K, CA 1.5. Okay, and I basically need to find XA2, right, in the CSTR, which is double or twice as big. So the CSTR, I need to use my CSTR performance equation. And for this guy, the CSTR performance equation is V over FA note is equal to tau over CA note is equal to XA over minus RA. In this case, minus RA is K, CA to the 1.5. So this is equal to XA over K, CA to the 1.5. Okay, so do I have CA? I mean, I can get it from XA1, right? But let's rewrite this in terms of conversion to make it easier for ourselves. So I know that CA is equal to CA note into 1 minus XA, right? So if I combine these two guys, I'm going to get minus RA is equal to K into CA note to the 1.5 into 1 minus XA to the 1.5. And I'm going to use this equation here. I'm using the first CSTR. So using the numbers for the first CSTR, I have V1 over FA note is equal to XA1, which is 0.7 divided by K. CA note is 10 to the 1.5 into 1 minus 0.7 to the 1.5. And then for the second CSTR, I'm going to have V2 over FA naught is equal to XA2, which is the entity I'm trying to find. K CA naught 10 to the 1.5 into 1 minus XA2 to the 1.5. And a common error, or an error some people did last time, is they did not explicitly write flesh out XA2 in the denominator here. It doesn't work because mathematically, for this problem to be mathematically valid, you need to have all your variables clearly expressed. You cannot sneak a variable through a problem. It doesn't work, right? Your variables have to be clearly expressed when solving problems. So again, I'm going to divide these two by each other. V2 is 2V1, so basically what? V2 over V1 is 2, so I'm going to divide the bottom one by the upper one. V2 divided by V1 is 2, FA notes cancel out, so I'm going to get 2 is equal to, these two guys cancel from here. This will be XA2 divided by 0.7 divided by 1 minus XA2 to the 1.5 divided by 1 minus 0.7 to the 1.5, which is equal to 0.3. 0.3 to the power 1.5. This is equal to 0.164. And so by 2 multiplied by 0.7, sorry, 0.3 to the power 1.5, right? Two multiplied by 0.7 divided by this is equal to 8.5, right? So now I can rewrite this expression as, so this will be 8.5 is equal to XA2 divided by 1 minus XA2 to the power 1.5, right? And now it's you just need to solve for this. You can iterate. Can you take a ln? I don't think you can take a ln. You have to solve this by iteration. And I think we solved it in the homework, so you need to iterate. And you're going to get 0.794 for XA2, right? And again, when it comes to iteration, on the test, if I give you an iteration problem, the answer will be very close to the original conversion. So if the original conversion of 0.7, your answer will be somewhere between 0.6 and 0.8. I'm not going to give you a very strange iteration. And once you close in on the second decimal point, you're good to go. Don't try to waste a lot of time trying to get an extremely accurate estimate of this conversion. You're just wasting your time on the test, right? Set up the problem. Tell me you're going to iterate. Try 1 or 2 iterations. That's it. You got the points. Move on. Okay. Save. Let's move on to the next problem. An aqueous feed containing A enters a 2-liter plug flow reactor and reacts away. Following this reaction, 2A goes to R and reaction rate is 0.05 Ca squared moles per liter second. Find the outlet concentration of A for a feed rate of 0.5 liters per minute. Okay, so I have a PFR, it's 2 liters. I have the reaction, second order, irreversible reaction. I'm given the reaction rate, and I need to find the outlet concentration for a volumetric flow rate of 0.5 liters per minute. Okay. And again, you have a lot of given, and take your time to sort of digest all of this equation, all of this, given information before tackling the problem, right? So don't panic, just take your time, absorb it, and should be able to solve it, which is this problem number 12. Yeah, this is problem number 12. Okay. Problem 12. And in this problem, I'm given a 2-liter PFR. The volume of the PFR is equal to 2 liters. I'm given an initial concentration of 1 mole per liter, so Ca naught is equal to 1 mole per liter, 2 moles, 1 mole per liter, sorry. I'm given the reaction is 2A goes to R, and minus RA is equal to 0.05 Ca squared mole per liter. Second, you're given a feed, a volumetric flow rate of 0.5 liter per minute, and you need to find Ca, right? You need to find the outlet concentration of A. Okay. So again, it's a PFR, so the first thing you need to do is write the performance equation of a PFR, right? So performance will be V over V naught is equal to Ca naught integral of 0 to xa final of dxa over minus RA. And you know, it really depends on your preference. I've seen some of you really like to work with the conversion expressions. If you're doing so, just be careful with the math. Otherwise, if you're flexible, you can always pick the more appropriate or the one which is going to make or reduce the chance of errors really when solving these problems. Minus Ca naught to Ca of dCa over minus Ra. So I'm going to use the second expression, and again I have an expression for minus Ra, which is 0.05 Ca squared, so this will be minus Ca naught to Ca of, actually it's going to be minus Ca naught over Ca of dCa over 0.05 Ca squared, and V over Va naught, I mean, I have, this is 2 liters, this is 0.5 liters. Let's integrate this expression first. So this, I'm going to take this constant out, 1 over 0.05 into integral of 1 over Ca squared is minus 1 over Ca, and I already have a minus here, right? This minus here. And I'm taking this from Ca naught to Ca. And again, just be careful with these minus signs. Just do it slowly. Don't panic, you know. So a lot of mistakes are made. Very basic. Anyways, so V is 2 liters. This is 0.5 liters per minute. This is equal to minus 1 over 0.05 into minus 1 over Ca plus 1 over Ca naught is 1. And this is basically 2 over 0.5 is what, 4. So this will be 4 is equal to minus 1 over 0.05 will be minus 20 into minus 1 over Ca plus 1. 4 divided by minus 20 is 0.2. So this becomes 0.2 minus 0.2 is equal to minus 1 over Ca plus 1. If you solve for this, you're going to get Ca to be 1 over 1.2, which is 0.33 mole per liter, which is the solution to this problem. And again, this type of problem it's not hard, just integration. Just be comfortable with your integrations, especially the simple ones. And, you know, don't do simple mathematical or arithmetic errors once you get to this stage. Okay, good. Problem 12 done. Let's move on to the next problem. Okay, so now let's continue. So now we're doing problem number 13, right? so in this problem, an aqueous feed of A and B, 400 liters per minute, 100 millimoles of A per liter, 200 millimoles of B per liter is to be converted to product. Okay. The kinetics of the reaction are represented by this equation. You're given a reaction rate. Which flow reactor type PFR or CSTR will require the smallest volume to achieve a 99.9% conversion of A to product? Okay, so again, we're looking for we're given an equation, we're given some kinetic parameters, and you need to find which reactor is going to give you the smallest volume. Okay, so at this stage, really, you should know directly that PFR is the smallest volume, right? You actually don't need to solve this problem numerically. So at this stage of the course, I expect, I mean, you can look up the solution if you want to, but since you're not explicitly asked the ratios or explicitly asked anything about, how much smaller or anything like that, a PFR will give you a smaller volume, right? To achieve the same conversion. And of course, you can always try to solve it numerically or not really. It doesn't matter. You're still going to reach this conclusion that the volume of the PFR will give a smaller volume. We've talked about this a lot throughout the course, and it's actually a very easy problem, right? When we solve this problem, if you look up your solution, I think it's in homework 3 or 4, we haven't really covered extensively, that the PFR will give you a smaller volume. So we actually solved for this volume and this and that volume using, the first performance equation, the second performance equation, going through, all the, plugging in the reaction rate expression, etc. And we still got the same answer. Okay, so just be careful for these types of problems. You use your knowledge, right? You don't have to reinvent the wheel every time. Anyways, let's move on from number 13, very basic problem. And let's move on to the next problem, problem number 14, right? Problem number 14. An aqueous reactant stream of 4 moles of A per liter passes through a mixed flow reactor followed by a plug flow reactor. Find the concentration at the exit of the plug flow reactor if in the mixed flow reactor Ca is 1 mole per liter. The reaction is second order with respect to A, and the volume of the plug flow unit is 3 times that of the mixed flow unit. Again, these are the types of problems. We have 2 CSTRs in series, 1 CSTR followed by 1 PFR, etc. And these are just an exercise in using your performance equations correctly, right? So let me get, so this is problem 14. And in this problem, you're given a CSTR followed by a PFR. And I'm given some metrics or some information in this problem. I'm given an aqueous reactant stream of 4 moles of A per liter. So it is Ca naught is equal to 4 moles per liter. And I need to find, so let's say this, you're given that Ca1 is 1 mole per liter, and we need to find Ca2 is equal to what? You're being told that the reaction is second order with respect to A, and the volume of the plug flow unit is 3 times that of the mixed flow unit. So volume of the PFR is 3 times the volume of the CSTR. Okay, and you're being told it's second order with respect to A. So your reaction rate kinetics minus RA is equal to K, Ca to the 1.5. Okay, so I'm looking for CA2. I have CA1. I have CA note. This guy here is a CSTR. This guy here is a PFR. So what am I really looking for? I need to find this K guy. I need to find this number right here. Once I have this number, I should be able to solve the problem, right? So if I get K, and I should be able to solve the problem. Alternatively, I could use this expression right here and divide the volumes of the reactor. So two ways to do it. You might think about it, and let's just go through the equations and see which one is going to be easier, right? So let's start with the first one. So I have a CSTR. The performance equation for a CSTR is tau over CA naught is equal to XA over minus RA. In our case, will be XA over KCA to the 1.5. Okay, so now I have tau is also unknown, so I'm going to multiply tau and K. Let's call this tau CSTR. So I'm going to have tau CSTR K. This is equal to CA naught, and again, this is CA1, right? Because this is the exit of the CSTR. So tau CSTR K will be XA CA naught divided by K CA1 to the power 1.5. Okay, so this is the expression I have here. So what's XA in this case? I have 4 going in, 1 coming out. XA is 0.75, right? You can always solve for it and get an expression, but we can solve for XA, right? So I have 4 moles going in, I have 3 moles reacting, so XA is 0.75. Okay, so we know XA is 0.75, we know CA naught is, CA naught is 4, CA1 is 1, so I can get an expression for tau 1 CSTRK, so this will be 0.75 into 4 divided by, actually, I don't need this K here, right? You already moved it up. So this will be CA1, which is 1 to the 1.5, 0.75 multiplied by 4. This is equal to 3, right? So tau CSTRK is equal to 3. So now let's do the same for the PFR. So for the PFR, the performance equation we said will be tau is equal to integral from CA naught, or in this case I have CA1 and CA2, so just be careful with these expressions as well, from CA1 to CA2 minus CA1 CA2 dCA over minus RA. So this will be minus integral CA1 CA2 dCA over K CA to the 1.5. Okay, is it 1.5? Where did I get this number from? 1 second. The second order with respect to A. Right? Yeah, problem 14, it's second order with respect to A. Not sure where I got this 1.5 from. 1 second. Let me just double check. We're not doing something strange. Okay, this is actually 2, right? Yeah, I'm not sure why did I write 1.5. But anyways, that's fine. Let's write the correct number here. So this is 2. So this becomes KCA. Let's just write this properly in all of them. So this becomes KCA squared. CA squared, this is 1, it doesn't matter. And here it has to be squared as well. So KCA squared. So now if I write this expression, I'm going to get tau is equal to minus CA1 is 1, CA2 is what I'm solving for, dCA over K Ca squared, and this will be minus 1 over K into minus 1 over Ca from 1 to Ca2, right? Again, integral of 1 over Ca squared is 1 over Ca. We're going to take K to this side here. Let's write this as tau PFR here. So I'm going to get tau PFR K is equal to minus into minus 1 over Ca2 plus 1, right? Plus 1 if I just plug the minus in there. So I'm going to get 1 over Ca2 minus 1. This is equal to tau PFR. So now I have an expression for tau CSTR, and I have an expression for tau PFR, and I have this volume right here. So usually, if you recall, we said we could use the tau over K to represent the volume, right? So tau K can be used to represent the volume. So using this logic, therefore tau CSTR, tau CSTR K over tau PFR K is equal to V CSTR over V PFR, and this is equal to 3. Right? V CSTR over V PFR is equal to 3. I'm going to plug in my expressions. So V CSTR K, I'm going to get 3 is equal to, sorry, this is correct. So tau CSTR K is 3. So I have 3 over 1 over Ca2 minus 1 is equal to 3, right? Let's just verify this. Volume of the plug flow unit is 3 times that of the mixed flow unit. Volume of the plug flow is 3 times. So yeah, so this expression is reversed, right? So the volume of the plug flow unit is 3 times that of the CSTR unit. So this is actually 3 CSTR, and this number right here is 1 over 3. Yeah, just be careful with these things. Might trip you. I mean, hopefully not. Okay, so this will be 1 over 3. So now if I just cross multiply, I'm going to get 9 is equal to 1 over Ca2 minus 1. So from here, I need this expression to be 10. So I can get Ca2 is equal to 10 mole per liter, right? And find the concentration at the exit of the plug flow, and this does it. So Ca2 is 10 moles per liter, and this solves the problem. So this is the solution to this problem. Again, when given a relationship between volumes, most of the time, I want you to use the tau K expressions from the performance equations and relate them to the ratio of the volumes to solve this problem. And this type of thing will very likely show up on your test. Okay, let's move on to the next problem, problem number 15. Let's open the problem set. Reactant A plus R. Let's bring this up. Let's make this. Reactant A plus R, should be A goes to R, right? Yeah, this has to be A goes to R. Just be aware of this. Maybe we can make it fancy, but anyways. A goes to R. Ca notes 26 mole per meter cubed, passes in steady flow through 4 equal-sized mixed flow reactors in series. Total space-time is 2 minutes. When steady state is achieved, the concentration of A is found to be 11,521 moles per meter cubed in the 4 units. For this reaction, what must be the equivalent space-time in the plug flow reactor to reduce the concentration from Ca note to a final CAF of 1 mole per meter cubed? So what it's asking is, how can we achieve the same thing in a plug flow reactor, and what's the required space-time to do so? Okay, let's go back to the whiteboard here. And this is problem 15, right? So I'm given 4 CSTRs. The reaction is A, goes to R. We're being told Ca note is 26 moles per meter cubed. This thing happens in 4 CSTRs. Okay, the total tau. So tau total in this case is equal to 2 minutes. This is Ca note is equal to 26. Ca1 is 1. Ca2 is 5. Ca3 is it 1? 11. Ca3 is 2. And Ca4 at the end is, sorry, 1. Right? And you need to find the equivalent tau PFR to achieve the same final conversion, right? So basically to reduce your concentration of the reactant from 26 to 1 mole per meter cubed, of course. And again, for this type of problem, I'm looking for a specific equation, right? And the equation I'm looking for is CSTRs in series. I'm looking specifically for this equation. I'm not looking for you to plug in 4 performance equations. I'm looking for a very specific equation, which is this one. Ca naught over CAF is equal to 1 plus K tau I to the power n, where n in here is not the order of the reaction. N is number of CSTRs. Tau I is equal to tau total divided by n CSTRs. Okay, so I'm specifically looking for this equation. Whenever I tell you, oh, you have 4 CSTRs in series, you have 50 CSTRs in series, I'm looking specifically for this expression. Go read your slides and recall, or there are a couple of slides after each other describing this system of equation. So anyways, tau I will be 2 minutes divided by 4 CSTR, so it's going to be half a minute. So if I plug in all my numbers in this case, I'm going to get Ca naught is 26, Ca final is 1, is equal to 1 plus K multiplied by 0.5 to the n, which is number of CSTRs. In this case, it's 4. And you can basically use this to solve for your for the value of K. And if you do this, you're going to get K to be equal to 2.516 second minus 1, right? So, and this type of problem has 2 steps. The first step, you use this equation for CSTRs in series. The second step is you're going to use the equation for the equivalent equation for PFR, right? So the equivalent equation for a PFR for a first order irreversible reaction. So PFR with a first order irreversible reaction will be performance equation is CAF over Ca naught exponential of minus K tau. You have the K, I'm looking for this tau PFR, I'm solving for this tau PFR. I know CAF, I know Ca naught, right? And it just becomes a very easy problem to solve. And again, these two are for Ca naught, CAF, CAF, Ca naught. Just be careful of what you're plugging in. Will be 1 over 26 is equal to exponential of 2.516 tau PFR. You solve for the tau PFR, you're going to get the answer, which is 1.3 minutes, about 1.3 minutes. And this is the equivalent space-time in a PFR to achieve the same conversion. Now, on the test, you might get something very similar, but instead, you're going to have a PFR with a second order reversible reaction, for example, or you're going to get a PFR with a nth order reversible reaction, and the logic is the same, right? The logic is that the performance of n CSTRs in series is equal to the performance of 1 PFR, right? So if I give you this same problem, right, I give you the same problem where I tell you CA naught over CAF is equal to 1 plus K tau I, or I tell you, oh, I have 5 CSTRs in series, these are the concentrations, and I have a second order irreversible reaction, and the second order reversible reaction has a reaction rate of minus RA is equal to K CA to the 1.5, or nth order in this case, or is equal to K CA to the 2. It doesn't matter. What you need to do is take this expression and take the performance equation of the PFR, get this ratio CAF over CA naught is equal to an expression for the nth order or for the second order. You take this equation, you equate these two guys, or you solve for K here, plug it here, and you get the new tau, okay? This is how it's gonna show up on the test. If you're listening at this point, this is gonna show up on the test, okay? So just know how to do it. Good, let me save this screen. Let's move on to the next problem. Problem 16, right? Okay. At present, we have 90% conversion of a liquid feed, N equals 1, CA naught is equal to 10 moles per liter, to our plug flow reactor with recycle to produce with recycle of product. Okay. If we shut off the recycle stream, by how much will this lower the processing rate of our feed to the same 90% conversion? This might show up on a multiple choice type of problem, just a theoretical understanding of how a recycle works. Well, let's go through this numerically for this problem. So let me write this down. We're doing problem number 16, right? So this is problem 16. In this problem, I have a PFR and I have a recycle for this PFR. I'm given some information. Let's write down the given. So I have conversion liquid feed. So we're being told N equals 1. CA naught is 10 moles per liter. Recycle R is equal to 2. If we shut down, so the question is asking if we shut down the recycle stream, by how much will this lower the processing rate of our feed to the same 90% conversion? Okay. By processing rate, so how much this lower processing rate, this basically means the tau. How much will the tau change? And this is not going to show up on the written portion of the test. Some concepts might be tested on maybe a multiple choice question, but we have other relevant things to really think about in this exam. But anyways, because it's a PFR, we need to use the performance equation for a PFR with recycle, right? So if you recall, performance equation, so PFR performance equation with a recycle will be, V over FA naught is equal to tau over CA naught. This will be equal to R plus 1 integral of R XAF over R plus 1 2XA final dXA divided by K CA naught 1 minus XA, right? And again, CA naught 1 minus XA, this is basically because it's a first order reaction, right? N equals 1, so minus RA is equal to K CA, which is equal to K CA naught into 1 minus XA. Okay, so now I'm basically looking for this tau with recycle, and I'm going to compare it to the tau without recycle. So if I plug in all these, if I plug in the numbers for this expression, let's have a look here. So the CA note is going to cancel the CA note. I'm going to take the tau k's. So I'm going to move the k to the side. So I'm going to get tau recycle k is equal to r plus 1 integral or xa f over r plus 1 to xa f of dxa over 1 minus xa. You do the integral, you evaluate everything, you're going to get your tau recycle k will be 3 ln 4, okay? And then I need to compare this tau recycle to the typical tau, the PFR. So tau PFR, to get this, because it's a first order reversible reaction, it will be CAF over CA naught is equal to exponential minus K. Tau, you do the math here, you're gonna get K tau PFR with no recycle is equal to ln 10. You get the ratio of this guy to this guy, and basically you're gonna get tau recycle over tau PFR is equal to somewhere around 1.8. Okay, that's how you solve this problem. Get the tau with the recycle using the performance equation with the recycle, and then you get the tau for the PFR just using the normal performance equation of the PFR. You divide these two expressions, you get the ratio, right? 1, 2, 3. And this is not going to show up on the test. If anything from the recycle is going to show up on the test, it's that as R approaches infinity, your PFR approaches a CSTR, right? If anything from recycle shows up on the test will be this point, and you just need to know this. As my recycle ratio of a PFR approaches infinity, the performance of the PFR will approach that of a CSTR. And this is in converse to having CSTRs in series. So as n CSTR approaches infinity, the CSTRs behave like a PFR, right? And these are really the two opposite ends of this relationship, where you have very well mixed system versus a very poorly mixed system. And you can use this, to define your parameters. But anyways, you're not gonna get a problem to solve a recycle on the test numerically. However, this type of relationship might show up on a multiple choice test. Multiple choice part, sorry. Okay, let's go back. Now we are doing okay, let's do number 17. The kinetics of the aqueous phase decomposition of A is investigated in two mixed flow reactors in series, the second having twice the volume of the first. So I have two CSTRs in series, the second one is twice as big as the first one. At steady state, with a feed concentration of 1 mole of A per liter and mean residence time of 96 seconds in the first reactor, concentration is 0.5, and in the second reactor is 0.25. Find the kinetic equation for the decomposition. So I'm given two CSTRs, I'm given the concentration, all the concentrations, I'm given all the residence times, and I need to find K, basically, right? So let's approach this problem here. Okay, showing the screen. This is problem 17. Problem 7. In this problem, I have two CSTRs in series. Right? You're being told that CA note is 1 mole per liter, and this is aqueous phase decomposition of A, right? A goes to R, and tau 1 is equal to 96 seconds. You're also being told CA1 here is 0.5 mole per liter, and CA2 is equal to 0.25 mole per liter. Are you given anything else? So given mean residence time in the first reactor. You're not given the mean residence time in the second reactor. However, you're being told that volume of CSTR2 is equal to 2 times the volume of CSTR1, right? So this sets up the problem here. And are you given the kinetics? Find the kinetic equation. So you're not being told that it's a first order expression. You actually have to solve or determine whether it's a first order or if it's an nth order expression in this case. So that's fine. I mean, it's not going to matter. So in this case, I have minus RA is equal to K CA to the n. If it's a first order reaction, it becomes a very simple problem. However, again, with these types of problems, Levenspiel does not make it very clear, but on the test, it will clearly specify nth order and to find n, right? Because it might be a bit confusing. It's not said, and you just assume decomposition most of the time is first order, but in some cases, just to be consistent with what we're saying. Anyways, so I have two CSTRs in series. What are we going to do? CSTR performance equation. So I'm going to use the CSTR performance equation. So for the first CSTR, I have V over FA naught is equal to tau over CA naught is equal to, you can calculate the conversions if you want to. I can just write it CA naught minus CA over CA naught. Again, this is the conversion multiplied by 1 over K CA to the n. And for the first CSTR, so what I'm going to do is I'm going to evaluate the tau over K and relate them to this volume. And again, whenever you have two reactors in series and you have a relationship between the volumes, I'm looking for the tau K type of expression. So for the first CSTR, I'm going to call it tau 1 K will be equal, so tau 1 K, CA naught cancels with CA naught, so CA is going to be tau 1K is equal to CA naught minus CA1 divided by CA1 to the n, and CA naught is 1, CA1 is 0.5, 1 minus 0.5 divided by 0.5 to the n, and this will be 0.5 over 0.5 to the n. Okay, and for the second CSTR, I'm going to do the same thing. So tau 2K will be now CA1 minus CA2 divided by CA2 to the n. And that's something, some of you confuse it when you have reactors in series. Again, for the second reactor, you're talking about CA2 and CA1 because the initial concentration in the second reactor is CA1. It's not CA naught. So be careful with this as well. Sort of a simple idea, but it can trip you up, right? So I'm going to get, in this case, CA1 is 0.5 minus 0.25, 0.5 minus 0.25 divided by 0.25 to the n. So I'm going to get 0.25 divided by 0.25 to the n. So I have this expression, I have this expression, I have this expression right here. So now I'm going to relate these two expressions with this given expression right here. So let's move on to a new sheet. Let's just go back and copy the expression. I have tau 1K, 0.5 over 0.5 to the n. So and we have now 2k 0.25 over 0.25 to the n, and we are being told that v2 is equal to 2, v1 is equal to 2, v1, and this basically means that v2 over v1 is equal to 2, and this is equal to tau 2k over tau 1k, right? So if I basically use all of these expressions here, so I'm going to get 2 is equal to 0.25 divided by 0.25 to the n multiplied by 0.5 to the n divided by 0.5, right? So if I just solve for this, this is 2, and you can always combine these two as well. So this will be 4, right? We're going to multiply 2 to this side. 0.25, this is 2 to the n, right? 4 is equal to 2 to the n, so n is equal to 2. You have the reaction order, or order of this reaction. And now we need to find k. And you can find k from this expression, actually. You know tau 1 is 96 seconds. So if you recall, tau 1 is equal to 96 seconds. So this implies tau 1k is equal to 0.5 over 0.5 to the n. So 96 into k is equal to 0.5 over 0.5 squared. So k in this case will be 1 over 48, because 0.5 over a quarter. So this is 2. 96, 2 over 96, 1 over 48. And you can get your units for this. I think it will be liter, second. Just verify these units. And then you have k, you have n. This solves problem 17 to solve for the kinetic weak expression. And again, on this problem, on the test, I will clearly tell you that it's an nth order reaction to solve for n. Okay, good. Let's move on to the next problem, and this will be problem 18, right? Okay, problem 18. A decomposes by irreversible first order kinetics. In a batch reactor, 35% of A is converted in a 7-minute run. When will it reach 85% conversion? Repeat for second order kinetics. Okay, this is an easy problem. This is problem number 4. Homework 5, right? So you're told that A, let's sorry, let's go back there, problem 18. A decomposes by first order kinetics, so you have first order, XA is equal to 0.35 when T is equal to 7 minutes. XA is equal to 0.85, T is equal to what? So we've done this type of problem a bunch of times today, but anyways, so I mean, there's a high probability this type of thing is going to show up on the test. Hopefully the hint is clear enough. But anyways, for first order, case number 1, you're going to get minus ln. 1 minus XA is equal to KT. I'm going to use the first set to solve for K, second set to solve for T. Alternatively, you can just divide the two cases, which is what I'm going to do. So I'm going to get minus ln 1 minus 0.35 divided by minus ln 1 minus 0.85 is equal to K into 7 divided by K into the time I'm trying to solve for. The K is going to cancel because it's a non-zero constant, right? So I'm going to get, if I get this expression, ln 0.65, right? divided by len 0.15. I'm gonna get a number, right? 7 divided by this number, you're gonna get t to be equal to 30.83. Okay, very simple. Now for second order kinetics. So again, second order, it's case number 2, right? For second order. And the logic is the same. Just have a different equation. 1 over CA naught into XA divided by 1 minus XA is equal to KT. Arguably, this might be a simpler form. But anyways, I'm going to divide the two expressions. So I'm going to get 0.35 divided by 1 minus 0.35 divided by 0.85 over 1 minus 0.85 is equal to K into 7 over K into T, which is what I'm trying to solve for. And if you just do the math here, you're going to get the T of 73.6, right? So you're going to get the T of 73.66 minutes. Very simple problem. This will show up on the test as one of the easy problems. So just be prepared. Don't do simple mistakes. I mean, again, it's one of the easy points. Okay. Moving on. Problem number 19. After 10 minutes in a batch reactor, reactant A is 55% converted after 27 minutes. Is 55% converted. After 27 minutes, conversion is 70. Find the rate equation to represent this reaction. Okay, so again, very similar problem. However, now I'm solving not for time, but for another type of expression. So let me save this. Let's go here. It's problem 19. And this is problem 5 from homework 5, right? Yeah, problem 5, homework 5. Sorry, let's write down the specification. So this is problem 19. Okay, so after 10 minutes, I'm given T1 is equal to 10 minutes, XA1 is 0.55, T2 is 27 minutes, XA2 is 0.7. You're being told that CA naught is 0.5 moles per liter. Find the rate equation to present this reaction. And you don't know anything about this reaction. You just know that it has A is being converted to something. So I need to find the order. So I need to find N and K, right? I need to find N and K. And we're going to assume that it's minus RA is equal to K CA to the power N, right? And we don't know anything about this, this unit, and we know it's in a batch reactor. So again, if it's an unknown order, so case number 4 for an unknown order. And the performance equation in this case, just, you can always derive it or you can know it. CA naught 1 minus N into 1 minus XA into 1 minus N, or possibly just do this, minus 1 is equal to N minus 1 KT, right? And this is the performance equation for this type of problem. And I have two sets of parameters for T and X, and I'm solving for two unknowns, N and K. So you can solve directly using two equations, two unknowns, if you want to, but what I'm going to do is I'm going to solve for n directly by just dividing the two scenarios or the two cases. And then once I get n, I'm going to back solve for k. Okay, so let's do this. So I'm going to get, I know C, I know it doesn't matter, C, I know it's going to cancel out. So I have 1 minus 0.55 to the 1 minus n minus 1 over 1 minus 0.7 to the 1 minus n minus 1 is equal to n minus 1k is going to cancel from the top and the bottom, 10 over 27. This is my functional equation. You need to iterate to solve this equation. So we already got the solution last time. So by iteration, n will be equal to 3.16. And you can always try not to waste time using Excel. If you have this already programmed in Excel, sure. If you don't, then don't worry about it. Just if you can do it by calculator, sure. Otherwise, if for some reason this shows up on the test and you need to iterate, or you find yourself in a situation where you need to iterate for some reason, try one or two numbers, tell me, oh, it's going in this direction, it will probably be between this and this, and then move on to the next one. Okay, don't waste a lot of time iterating. And again, you're not going to get an iteration problem. And if you get an iteration problem, the answer will be clear. It will be either 3, 2, maybe 1 point, no, 3 or 2. It will be either 3 or 2. Okay, I'm not going to give you a problem with decimals or anything like that. If it shows up, I haven't decided if it will or not. Okay. Anyways, so you have your n, plug it in here, and you get k, right? So plug it back into any plug it back into plug it back to get k, right? Hopefully this is clear enough. Again, very simple problem. The logic is straightforward. However, the iteration and the math can be lengthy. On the test, again, you're not gonna get to this type of thing. Okay, let's move on. Okay, so this is the maximum here. Okay, let's save all these guys. Save 20 PNGs. Oh, so every time I save, it saves. Okay, let's clear all drawings. And wait. One second. Okay, let's move on. Problem 20. Know the differences between IBR, CSTR, PFR. Yeah, so you can read this from your slides. Again, just this might show up on a multiple choice question. Make sure you know the fundamentals of the 3 types of reactors: plug flow, continuously stirred tank reactor, batch reactor, you know, performance equations, all the stuff, what the variables means, etc. Okay, let's move on. Problem 21. How many problems did I assign? 31. Okay. Problem 21. The reaction A to R with the following reaction kinetics minus RA is equal to K Ca to the power N is carried out in a CSTR with a conversion of 60% and initial concentration of 1 mole per liter. If the volume of the CSTR is doubled while keeping the same flow rate, determine the new conversion for different values of your reaction rate constant. Okay, let's start solving this problem. Okay, so this is problem 21. and you're being told that A goes to R and minus RA is equal to K CA to the power N. You're being told that CA naught is 1 mole per liter, XA is 0.6, and you're being told that the volume of the CSTR is doubled. So V2 is equal to 2 V1, volume of the CSTR is doubled. Determine the new conversion. So let's call this XA1, find XA2, basically. Okay, again, the starting point will be the performance equations for the CSTR. All right, so you start with the CSTR performance equation. So I have V over FA naught is equal to tau over CA naught, which is equal to XA over minus RA. And in this case, it will be XA over K CA to the power N. I can rewrite this in terms of conversion. So it'll be XA over K CA naught to the power N into 1 minus XA to the power N. Right, so since I have volume, so I need to relate the tau K. So I can rewrite this as tau K is equal to XA divided by CA naught to the power N over 1 minus XA to the power N. And I have tau K1, tau K2, XA1, and I need to find XA2 in this case for different values of N, right? So if I know that V2 over V1 is equal to 2, this is equal to tau 2K over tau 1K, and this will be basically XA2. So this will be XA2 divided by CA naught does not change, and since I'm dividing, it's going to cancel out 1 minus XA2 to the power N multiplied by 1 minus XA1, which is 0.6. So this will actually be 0.4, right? So one will be basically 0.4 to the power N divided by 0.6, right? And now if N is equal to, you're given a bunch of N's, right? N equals 0.5, 1, and 2. Just plug in your numbers. So N is equal to 0.5, N is equal to 1, N is equal to 2. For each of these three cases, just plug in N here and you solve for XA2. Very straightforward problem. You can continue from here. So let's move on to the next one. Problem 22. An aqueous reactant stream passes through a mixed flow reactor followed by a plug flow reactor. Find the concentration at the exit of the plug flow reactor. If in the mixed flow reactor CA is equal to 1 mole per liter, reaction is second order with respect to A, and the volume of the plug flow unit is 3 times that of the mixed flow unit. I feel like we've solved this before. Yeah, so this is exactly like problem 14, actually, right? Okay. So problem 21 is exactly like problem 14. Second order, second order. Yes, 22 and 14 are actually identical. I mean, you don't need to resubmit them together, but that's how it is. Yeah, just don't submit it twice, just write same as problem number 22. Problem number 23, let's move on. Reactant A goes to R, passes in steady flow through 4 equal size CSTRs. Okay, so this one's also similar to, is it similar? Yeah, this is similar to problem 15, right? So problem 23 is the same as problem 15, and this guy has to be 26 actually. But yeah, this problem 23 is the same as problem 15. Okay, that makes things a bit easier. Problem 22, same as problem 14, problem 23, same as problem 15, right? Okay, anyways, let's move on with this problem set. Problem 24, this showed up on your exam action. It's identical to one of the problems on your, it's identical to one of the problems on the slides, actually, right? So you're given a feed of pure A, and so this is problem 12 from homework number 8, if you recall. And we've already solved it, but let's go through it again, just for the sake of practice. And this showed up on your test anyways, but so for problem number 24, the reaction A to R, you're given some thermodynamic details that gives free energy, the enthalpy of reaction. You're being told that CPA is equal to CPR, and you're given some experimental data for temperature, for time, and for conversion, right? And you're being told that given a feed of pure A, determine the following temperature range needed to achieve a minimum equilibrium conversion. You need to explain the difference between equilibrium and actual conversion, determine the activation energy for the forward and backward reaction, and outline how to plot the conversion versus temperature chart. And again, this has been solved in homework number 8, but we can go through it again. So in this problem, so this is problem number 24, right? So for problem number 24, okay, so for this problem, we're given some thermodynamic data. Let me erase this guy right here. Let's do it properly, give ourselves some space. Again, this is so I'm given A, K1, K2 goes to R. I'm given two parameters, delta G at 298 is equal to minus 15,000 joule per mole. And I'm given delta H, note at 298 is minus 60,000 joule per mole. And you're also told that CPA is equal to CPR. You're given two sets of information. You're given temperature in degrees Celsius, time in minute, and conversion. Temperature is 70 Celsius, 35 Celsius, 3, 12.4, and 0.8. And at this stage, it's always good to convert this to Kelvin because most of the equations have to be solved in absolute terms. So this is 334 Kelvin, and this is 308 Kelvin. So number one, you need to find the temperature range. For number one, you need to find temperature range for XAE to be at least 0.8. So at least 0.8, or to achieve the minimum XAE of 0.8. So this means that XAE has to be greater than or equal to 0.8. And again, this is the same as the example in your book. And you start off always, delta G is minus RT ln K. And this is the capital K, and you need to make a distinction here between the capital K, which is the thermodynamic equilibrium constant, and similar to what we wrote in the solutions before, I'm gonna denote this with sort of a line across the top, and the small k here, this is your reaction rate constant, right? And they are different ideas, and you have to be careful which one you're solving for. RT ln K, you have your G, temperature in this case will be 298, right? 298 Kelvin. You solve for K, you're gonna get a K at 298 equal to 425.9. Okay, and your thermodynamic equilibrium constant is dimensionless, right? Because this is equal to K1 over K2. And because the forward reaction and the backward reaction are both first order, then it's dimensionless. If forward reaction is a certain order and the backward reaction is different order, your units are gonna change, okay? So once you get the K, I'm gonna get an expression for K as a function of temperature. So I'm gonna get ln of K2 over K1 is equal to minus delta H over R 1 over T2 minus 1 over T1, right? I can denote T1 to be 298 and K1 will be the K at 298. So I can use this expression to get ln K2 over 425.9 is equal to minus delta HR, which is given here. So minus of minus, this will be 60. And again, minus of minus. So this entity here will be positive, right? 8.314 into 1 over T2 minus 1 over 298, right? So now I have a function K as a function of T. This is my first equation or first expression. K as a function of T, okay? And now the second thing will be to use the definition of K. So you can call this maybe step 1, and then step 2 right here will be to use the definition of K to get a relationship between K and conversion. So by definition, because it's a first order reversible reaction, K is equal to XA equilibrium over 1 minus XA equilibrium, right? And this becomes my second expression, which is K as a function of XAE. And I'm going to use these two expressions with each, I'm going to use these expressions in parallel to get the temperature at which I have an equilibrium conversion of 0.8, right? So now the logic becomes I have XAE is equal to 0.8. Use this to find K, and then you use this to find the temperature, right? And because the reaction is exothermic, you want to operate at temperatures below the temperature, this temperature you find. If the reaction is endothermic, you want to operate at temperatures above this temperature, right? And if you do the math, it will make sense. If you create a table similar to what we have in the slides, it will make sense, okay? So this is how you do the first part. Explain the difference between equilibrium and actual conversion. Equilibrium conversion is, you give your system time to reach equilibrium, right? So, if I have a reaction, I let it go to completion. If it's irreversible, if it's reversible, I let it go until it reaches its equilibrium, where basically my forward reaction and my backward reaction are equal in rate. The actual conversion is what actually happens in your reactor. So inside your reactor, sometimes you don't reach conversion, you don't reach equilibrium, right? Material are zipping through at a certain flow rate. You have this and that, you have all these mixing elements, you have your baffles, you have your catalyst, a lot of things happening. So you might not actually reach your equilibrium conversion. However, you will reach an actual conversion. Okay, what else? Okay, so number 3, determine the activation energy. So this is problem number 24 continued. Determine the activation energy. And again, to get the activation energy, the approach is straightforward and is similar to what is shown in the previous solution. So I'm going to use this expression or this equation here. So I know K1T over XAE is equal to minus ln 1 minus XA over XAE. If you're wondering where I got this from, this is for case number 6, which is first order reversible reaction, right? This is the performance equation for that case, okay? And you're given two sets of experimental data, as you mentioned in the earlier slide. You're given 73.4, 35, 12.8. You're gonna plug them in here. So if you plug them in here, if you plug the first set of parameters in here, you're gonna get plug the first set of parameters in here, you're gonna get let's see, so I have t equals 3, and the actual conversion is 0.4. So I'm gonna get k1 into 3 over XAE is equal to minus ln 1 minus 0.4 over XAE. And then similarly for the second set of parameters, k1 into 12 over XAE is equal to minus ln of 1 minus 0.8 over XAE. So I have my two parameters in this case. And then I'm gonna get XAE from these two equations. So if I solve for these two equations and I get the XAE value, so I have an expression relating K1 to XAE, and what I really need to do at this step is to determine XAE, right? So if I know for this case, time XA, and I have a temperature as well, 0.4, and we said the temperature is 70 Celsius, which is equal to 343 Kelvin. I can use this temperature and use the two equations we derived earlier. So if I use this temperature, plug it in here, get a value for K2, and then use this value to get an expression for XAE, I can get a clear definition here. So here, using these sets of parameters, I can get my K2, or my equilibrium, you don't really need this to, can get the K to be equal to 17.76, and XAE to be equal to 0.95. Similarly for the second conditions where I said it's 12.8 and the temperature was 35 degrees Celsius, which is 308 Kelvin. Using this, you can get a value for K to be equal to 194.01 and a value for XAE to be equal to 0.995. Okay, so now I have K and XAE for the two scenarios. And I can get now, if I plug this XAE here, I can get K1 at the first temperature, I can get K2 at the second temperature. So if I plug these two guys in here, you know, if I plug this here and plug this here, I'm gonna get basically K1 is equal to 0.173 at Kelvin, and then for this guy here, I'm gonna get K1 to be equal to 0.134 at temperature is equal to 308 Kelvin. Okay, and now you're gonna use this these two expressions here with the equation that K is equal to K naught e to the minus EA over RT to get basically an expression for, or a value for EA for this problem. Okay, so basically you have two conditions, you have two unknowns, K naught and EA. You can either solve for both of them, or you can just divide them and solve this problem. And this is similar to what we've done, and this is shown on your slides. You can go and revise them from your slides as well. And this showed up on your last test. The likelihood that this type of problem will show up on your next test as well it is not high. However, it's good to know how to solve and just be prepared just in case, right? You never know. Anyways, let's move on to the next problem. Problem number 25. Um, Good problem number 25. Liquid reactant A decomposes as follows: RRKCa squared or SK2Ca. A feed of aqueous A enters the reactor, decomposes, and a mixture of A, R, and S leaves. Determine the output concentrations of R and S for a conversion of 75% in a CSTR, and determine the output concentrations of R and S for a conversion of 80% in a PFR. Okay. And this problem is actually identical to this showed up on your test, except there was a slight twist, right? Instead of having CA squared, you had CACR, and you had to do a quadratic to solve the problem. And the approach is really the same for all these types of problems. This is similar to problem number 10 from homework number 8, right? Let me just verify this. Yeah, this is similar to problem number 10 from homework number 8. So let me share the solution from homework number 8, which was uploaded. And let's see. So for these types of problems, this is really how you do it. And again, a lot of you were able to do it on the test. A lot of you were comfortable. I don't think this was a problem or an issue for most of you on the test. So if you're having a hard time, if you don't see it, just send me an email and we can schedule a meeting. There are no office hours, but I'll be available to talk about this as well. And I'm gonna stop here. This lecture has gone over 2.5 hours, but basically the remaining problems on your homework set are all taken from the last two homeworks, right? So if you're a lot of you seemed very comfortable on exam 1 or sorry, exam 2 with a lot of these problems, so that's good. So I'm not going to go over them. You can just read the solutions which have been posted and come back with questions. And the last couple of problems are taken from the last homework. This will likely show up. A problem similar to 30 or 31 will almost certainly show up on your finals. So just be prepared to do them. If you're not clear on how to do them, send me an email. We can talk. We can schedule some hours to meet and talk about this. Anyways, I'm going to stop here today. And again, study. If you have any questions, let me know. And I'll be available over the break or anytime before the test to discuss or to answer any questions. Thank you very much.